Just quickly recall what was the law of large number that we have seen already and also proved in one version. So this was the main idea, that if I give you x1, x2, etc. IID, so it is like rolling the same die again and again or tossing the same coin again and again independently such that expectation is mu. I had just written I, so because they are IID, all of them have the same expectation, I have called it mu. So I am assuming that is a number in R. Then if I take the averages of the first n of them, then these things go to mu as n goes to infinity. Now this is stated in a rather loose way because I have not made it precise what is meant by this convergence, but intuitively this is the thing that first set the ball rolling for probability, namely that was the first mathematical version of what we call statistical regularity. So all these things are random, so as you increase n, more and more randomness are piling up, but when you take average, somehow the randomness kind of dissolves away or cancels itself out and you are approaching a number, fixed number as the limit. And Bernoulli had proved one version of this where he made this convergence precise in the following sense. He took these two quantities, looked at their difference and saw when does this thing is more than some epsilon. And he took the probability of that and showed that this goes to 0. And this goes to 0 not only for one epsilon, but it does so for all epsilon greater than 0. And in order to prove this, he had made another assumption that the variants of xi's are also finite. Now, it is possible to make this convergence precise in other ways, and in fact, it is also possible to drop this assumption, but we are not caring about that. We are caring about the main idea that if you take lots of IID things, then if you take average, then they should converge to a constant. So graphically, if I show n here and this quantity in the vertical axis, in that case, if I take points, I will find that initially things will possibly fluctuate and then eventually it will just stabilize and approach a fixed value that will be mu. Now in case of the Cauchy distribution, this is undefined because expectation is undefined, and we are going to see that the Cauchy distribution actually defies this behavior. We cannot say that a law of large number is false because law of large number had made this assumption, which is not true for the Cauchy distribution, but this behavior simply does not hold. There is no such convergence as we are going to see in a demonstration now. In this video, we shall see how the Cauchy distribution baffles the laws of large number. We shall use simulation. We shall simulate 10,000 observations, IID, from some distribution. Initially, I will do it from the exponential distribution with rate 1. Then I will find out the cumulative means. For this, I will use the cum sum function and divide it by the running sample size 1 to up to n. So y will store the cumulative sums and then I will plot it. So let us see what we get. I get this where you can easily see convergence to 1, which is as expected because if exponential has rate lambda, in that case the expectation is 1 over lambda, so 1 over 1 is 1. Now if I do the simulation once again, I will get a completely different thing at the beginning, but again we have the same convergence to the same value. I can change it to some other distribution. For example, I can do it for the uniform distribution for say from 2 to 4. In that case, I will again get convergence now to 3, which is the expectation. If I do it again, I will again get convergence to 3, though the initial ups and downs are quite different. Now, we shall come to the Cauchy distribution. I will do exactly the same thing. Let's see what we get. Well, it does look like it is something like a convergence, but let's do it once again. And now the convergence seems to have just vanished. Even if you say it converges, it is possibly coming towards 5. Earlier it was coming to 0. Let's do it once more. And again, it shows a weird behavior. Let's once more. And yet another behavior which is now near to 50. So you can see that we are not having any convergence. But of course, this is just a finite demonstration because we worked with finite sample size. That's what a computer can manage to do. In order to really prove that the convergence is not there, we need to proceed theoretically. In order to explore the behavior of the average of the first n xi's in a IID Cauchy sequence, we shall start with this theorem. The theorem says if u and v are independent Cauchy and alpha is any number between 0 to 1, any fixed number, then this convex combination of u and v, alpha times u plus 1 minus alpha times v, that will again have the Cauchy distribution. Now it is not very difficult to prove this using the machinery that we have already developed. Number one, we can use the Jacobian formula to find density of this, Jacobian for density of this. We know how to find out the density of sum of two random variables, convolution, or we can directly use the characteristic function method, which I am going to do here. I just call this x. Then for t in R, I want to find out the characteristic function of x. If I can somehow show that this is this, then I am done because I know that this is the characteristic function of Cauchy distribution and characteristic function characterizes the distribution. So I will just expand it. Like this, I have merely replaced x by its full definition. I have just distributed this it to both the things. Now by property of exponential function, this is e to the power this times e to the power that. Now I have assumed that u, v are independent, so this being function of u alone and this being function of v alone, they are also independent. And we know that the characteristic function always has finite expectation, so we can always have, the characteristic function always exists finitely, so this thing always has finite expectation. So expectation will now split over and I will get this. I immediately recognize this as the characteristic function of u evaluated at t alpha. I know characteristic function of Cauchy is e to the power minus mod t, so this one will be e to the power minus modulus t alpha. Similarly, this one will be e to the power minus modulus t times 1 minus alpha. And you combine them to get this. Now you might feel that you are stuck because how can I add two moduluses? It is here that the fact that alpha lies between 0 and 1 is going to help. So this alpha and 1 minus alpha both can comfortably come out of the modulus sign, giving mod t times alpha and again mod t times 1 minus alpha, and these things nicely cancel to produce our required e to the power minus mod t exactly as we wanted. Now we shall use this theorem to explore what we wanted to explore, namely I have a sequence x1, x2, x3, etc. IID Cauchy, and I am interested in exploring the behavior of xn bar, which is defined as this, average of the first n of the xi's. Now let's take a look at n equal to 1, you get x1, which anyway is given to be Cauchy. Now what is x2 bar? That is average of x1 and x2. So it is half of x1 plus half of x2. This is very much like this. x1, x2 are independent Cauchy and the role of alpha is playing by half. So you immediately see that this fellow must again be a Cauchy random variable. Now let's go into x3. x3 bar is average of the first 3, but I will think of it in this way. I am taking x2 bar, multiplying that with 2. This will give me x1 plus x2, and with it I am adding x3. So I have now added all of them. I am dividing the entire thing by 3, which means it is actually a convex combination of x2 bar and x3, the weights being 2/3 and 1/3. But again I can appeal to the same theorem, because x2 bar being a function of x1 and x2 alone, and x3 being here, so they are all independent, and I am forming a convex combination. The role of alpha is placed by 2/3, so 1 minus alpha is 1/3, so again this is Cauchy. And continuing in this way, you can see that all these things will be Cauchy. Now this result actually shows why things were not really converging to any constant, because howsoever many observations you take, the average is just as random as your original random variable x1. So that is why things are not converging to a constant. Now in this exercise, you are to explore whether you need the condition alpha lying between 0 to 1. So again the same setup. I give you 2 independent Cauchy, but now I take alpha equal to 2, and your job is to check if alpha u, that is 2u, plus 1 minus alpha v, that is minus v, whether that is Cauchy or not. So all that you have to do is to compute the characteristic function and check if it matches the characteristic function of Cauchy, and I quickly remind you that this is the characteristic function of the Cauchy distribution.